Starting chapters 12 and 13, we're going to talk about gravitational forces and gravitational fields. So I'm going to do a brief introduction of Isaac Newton and kind of his discovery of gravity and what he thought about it. So to start out, we just are going to think about things we already know. We already know that forces are needed to change the speed or direction of an object. So when an apple falls out of a tree and accelerates to the ground, speeds up, we know that there has to be a force acting on it. And Isaac Newton knew this as well. The other thing, though, is that if forces are needed to change direction, then we understand that forces are needed for circular motion, right? And that's our centripetal force that we just took a test on. So if the moon is orbiting the Earth, there has to be a force acting on the moon, allowing it to orbit. Okay, so a force has to be acting on an apple to pull it to the ground. A force has to be acting on the moon to change its direction. And all of these are if you will, invisible forces, forces that you don't actually see direct contact between two objects. Okay, so I'll pause the video real quick and I'll write down what I just talked about. So when an apple falls, a force is acting on it. The moon in orbit around the Earth has a force acting on it. Both those things we know are true. So this force comes from Earth. Gravity pulls the apple to the ground and holds the moon in orbit. Right? Both those forces come from the Earth. So if I look at a diagram real quick, so if this is Earth and the moon and an apple, I see that the apple is pulled to Earth by the force of gravity. The moon is also being pulled by Earth towards the center, right? And the moon is in this circular motion here. Alright, so if I look at the orbit of the moon around Earth, just like this, circling Earth, picture drawn perfectly to scale, I have the moon orbiting Earth, and that force, this force of gravity right here, right, there's a force of gravity acting on the moon, pulling it to Earth. Here's the force of gravity acting on the apple, pulling it to Earth. It's both the force of gravity. When I look at it specifically for the moon, I see that this is a centripetal force. Right, so with the moon here, I have a centripetal force. So the force of gravity is actually causing circular motion. So the moon falls around Earth, while an apple falls into Earth. So if we think about in a little bit more detail why this is, and we'll actually get into a lot of detail of this if we touch on in chapter 14. So the moon has enough speed such that it falls around Earth. So if I look at the moon's velocity, the moon wants to go off on a tangent, right? It wants to go off in this direction, but gravity pulls it closer to Earth. So it is actually falling around Earth. Without the force of gravity, it would go off on a tangent and move away from Earth. So every time the force of gravity pulls it inward, it's pulling it closer to Earth than it otherwise would. Just like when the apple falls out of the tree, it falls closer and closer to Earth than it would if there was no gravity. So if I make a write out a statement there, I can basically say that the moon is going fast enough that it falls around Earth and the force of gravity only changes its direction, right? So that force of gravity is a centripetal force. It changes the direction but not the speed. So if I write out a couple more statements just to kind of summarize this in general about anything in orbit, not just necessarily the moon, but any planets that are in orbit, the sun that's in orbit in our galaxy, all of those types of things, I can write out another statement. So my general statement then is that objects with enough tangential velocity will be held in orbit by the force of gravity. Right? So if they're going fast enough, the force of gravity, a centripetal force, holds them in orbit. So if you think about what if the moon were to slow down, or even to the extreme, what if the moon were to suddenly stop? then it would just be an apple dangling from a tree that's going to get pulled to Earth. So if an object like the moon slowed down too much, it would be pulled into Earth, right? If the Earth were to slow down too much, it would be pulled into the sun. But right now, the Earth, the moon, the other planets, they all have enough tangential velocity to be held in orbit by the object that they're orbiting. Okay, so this is very conceptual about the idea of gravity, but I'm going to pause it and start thinking about how we actually calculate the force of gravity between any two objects, not just objects on Earth, but any two objects anywhere in the universe, and the force of gravity between those objects. So if we talk about gravitational force, if we just take a quick step back and remember what a force is in general, a force is an interaction between any two objects. So to have a force, I need two objects interacting. A gravitational force is an attractive force between two masses, and it's directed towards the center of gravity of each mass. Okay, so if I have two objects, they're going to have a gravitational pull between them. So right now, the Earth and me, there's a gravitational force between us. Right now, you and your computer, there's a gravitational force between you, right? Any two masses have a gravitational force between them. If we think about these two masses, then this little mass and the bigger mass, the way I have them drawn, they're pulling on each other, right? And they're pulling on each other in a direction towards their center of gravity. So the big mass is pulling on the little mass. So I have a force on the little mass towards the big mass. I have a force on the big mass towards the little mass, right? And so if I think about these two forces and I compare them, the force on the big mass compared to the force on the little mass is the same. Action equals reaction. So little m pulls just as hard on big M as big M pulls on little m. Right, those forces are equal and opposite in direction. So for example, right, we remember that if Earth pulls me with, let's say, 700 newtons of force, so what have I just told you about myself? If I told you that Earth pulls on me with a force of 700 newtons, I've given you my weight, right? Force of gravity, weight, same thing. Earth pulls me with a force of 700 newtons. So then how strong do I pull Earth? So I pull Earth with a force of 700 newtons. If I was more massive, what would happen to the force between Earth and me? It would get bigger, right? If Earth was more massive, what do you think would happen between the force of Earth and me? It would also get bigger, right? If I'm on the moon, do I weigh more or less on the moon? I weigh less. Why? Not because my mass is different, but because the moon's mass is different. So the gravitational force is an attractive force between two masses, and the strength of that force depends on the mass of those objects. Okay, so I'm going to write out this idea of calculating the gravitational forces between two objects, and it's going to be a statement that's pretty much common sense, but then we're going to formalize it into Newton's universal law of gravity. So Newton's universal law of gravitation, if I formalize kind of the common sense statement that we put in purple up above, Newton's universal law of gravitation says that the force of gravity between two objects is proportional to the product of their masses and inversely proportional to the distance between them squared. Right? That's kind of a long law, but it's just saying that the two masses, if they get bigger, the force of gravity gets bigger. If the distance between the objects gets bigger, the force of gravity gets smaller. And that's an inverse square relationship, so that if the distance doubles, if I'm 2 times farther away from Earth, my weight would be 1/4 as much If I was 3 times farther away from Earth, my weight would be 9 times as much. So it's inversely proportional to the distance between them squared, and proportional to the product of the masses. So if the one mass increases, the force between them increases. Okay, so this is a law of physics. This is not something that you get to just forget. This is something that you know will be asked at some point. Right? Newton's universal law of gravitation. So if I write this out mathematically, right, if I think about this mathematically, let me kind of scroll down and just leave this part here, then what ends up happening is we start to think, okay, the force of gravity is proportional to, that little fish looking thing means proportional to the product of their masses, so m times m, right, the two masses interacting, and inversely proportional to the distance between them squared. So when we think about things that are proportional, we're thinking about this like the area of a circle. So the area of a circle is proportional to what part of the circle? The radius, right? And specifically, the area of a circle is proportional to the radius squared. So if the radius of a circle doubles, the area quadruples, right? This is my idea of proportional. If I want to write out what the area of a circle equals, then I need a constant of proportionality. And that constant is the number that we're all familiar with. It's pi. It's just a number. The area of a circle equals pi r squared. So the force of gravity is proportional to the product of the two masses and inversely proportional to the distance between them squared. It's equal to, my constant of proportionality here is a capital G times m divided by d squared. Okay, so this is similar, where my G, right, this here is very similar to pi, right? It's just a number that makes my proportionality an equality, right? So let's talk a little bit more about what G is. G is the universal gravitational constant, or sometimes called the universal constant of gravitation. Okay, and it's just a number. It's just a number. It's a number that you'll need to remember. It's not a nice number. It's a really, really small number, because gravitational forces are actually not very strong at all, right? Wherever you're sitting, pick something up, right? You defied gravity. Gravitational forces are not that strong. So my universal gravitational constant is 6.67 times 10 to the negative 11th. It does have units. We're not going to be too concerned with the units, but I'll put them on here for now. Okay, 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Right? So this is written in scientific notation. It's written in scientific notation because I don't want to write out all 10 of these zeros before my 6. Right? That would be that number written out, not in scientific notation. So since it's times 10 to the negative 11th, I move my decimal place over 11 spots to make the number small. Right? So this is an equation, again, just like the law of universal gravitation. We're going to need to be comfortable working with this equation. Right? And we'll have practice working with it, and we'll look at it in class and practice using our calculator. So you are going to need to bring a calculator to class every day, because these are going to be calculations that you cannot do in your head. All right, if we think about the forces that we're going to be calculating, we're going to be calculating the force of gravity between the moon and Earth. So these numbers are going to be the mass of Earth times the mass of the moon divided by the distance between them squared. Right? These are things that you will need to have a calculator to calculate. Right? And if you remember, I'm not letting people borrow calculators anymore. Okay? So I'm going to pause it. I'm going to write an equation out, write an example out, and show you how to go through one of these calculations. And then we'll be done. Alright, so let's just go through one example. I'm going to ask you to calculate the force of gravity of a 4 kilogram object on the moon. Okay, so my force of gravity equals the universal constant times one mass times the other mass divided by the distance squared. So think about the values that I need here. Okay, the force of gravity, the two masses interacting. What are the two masses interacting? It's the 4 kilogram mass and the moon. So my universal constant, 6.67 times 10 to the negative 11th, multiplied by the mass of the moon. Okay, the mass of the moon, what's the mass of the moon? 7.4 times 10 to the 22nd kilograms. That's the mass of the moon. So that's one mass. It's interacting with a 4 kilogram mass. Right? So there's the product of the two masses interacting, and then inversely proportional to the distance between them squared. So what's the distance between this 4 kilogram object and the moon? Well, it would be whatever the radius of the moon is. Okay, the distance between them. If I'm on the surface of the moon, the distance that I calculate with is the radius of the moon. It's between me and the moon's center of gravity. So the radius of the moon is about 1.7 times 10 to the 6th meters. And I need to square that. I can't forget to square that. Okay, so let me just real quick, I'm going to label these. This is the mass of the moon. This is the mass of the object that the moon is interacting with. This is the radius of the moon. Alright, now before I put the answer on the screen here, let's just think about this. I want to calculate the force of gravity on a 4 kilogram object on the moon. What am I asking you to do? I'm asking you to calculate the weight of 4 kilograms on the moon. The weight of 4 kilograms on Earth is what? 40 newtons, right? So on the moon, I should get an answer less than 40 newtons. Should I get an answer like 0.0007 newtons? No. Things on the moon weigh a little bit less than they do on Earth. So I should get a number somewhere between, I don't know, 4 newtons and 40 newtons. Okay? So I'll go ahead, I'll put the calculation in my calculator. I'm going to put in 6.67 times 10 to the negative 11th times 7.4 times 10 to the 22nd times 4, and then divide that whole thing by 1.67 times 10 to the 6th quantity squared. I get that the force of gravity is equal to 6.8 newtons. So that is how much 4 kilograms weighs on the moon. That's the weight of 4 kilograms on the moon. So your homework for tonight, now that we've kind of talked about gravitation, talked about the law of gravitation, and even gone through a whole calculation using the universal law of gravitation, I want you to do chapter 12, questions number 1, 2, 7, 10, 14, 15. Okay, practice using these numbers in your calculator. It's really easy to type something in wrong, to make a mistake. I would say practice exactly with these numbers, this example, and see if you get 6.8 as your answer. Okay, if you're not, come to class and ask me some questions about what you might be doing wrong with your calculations. Okay, number 15 on the homework is another calculation that is for a 1 kilogram object on Earth. So you should be able to go through that whole calculation and the answer that you get should make a whole lot of sense to you. Okay, so 20-minute video, a little bit over, still better than a 45-minute class. So hopefully this is helpful and can get you through this assignment, and then tomorrow we can just jump right into gravitational fields and doing some more examples with these calculations. Okay.